All right, so let's start. We have one last talk for today. So Julian was speaking last year, lightning talk sessions, and his talk was chosen one of the two best talks. So he gets half an hour or maybe 35 minutes now to talk about streaming SQL.
Thanks, Jacek. Hello, everybody. I want to reiterate what Jacek said before the break. Vote for lightning talks, because if you don't, this is what happens. So, hope you all enjoyed your ice cream. I'm Julian Hyde. I'm an architect at Hortonworks. I come from a background in databases. I started off at Oracle. These days I'm very much involved in Apache and open source. So I have interest in implementing database systems, implementing query optimizers. Last year, for those of you who are here, I gave a talk about Apache Calcite, which is a query planning framework. It's part of the Hadoop ecosystem. It's kind of you can think of it as a toolkit for building a database. So there'll be some talk about Calcite today, but I'm talking about a kind of a broader initiative to achieve a consensus on how the SQL language should be extended to support streaming data. So there's a lot of streaming data around these days, and in fact we are starting to view data which was streaming all along. We are starting to view a lot of data through that lens. You've got IoT, sensor devices are producing what could be viewed as streams of data. Within the data center, Kafka is, I think, rapidly becoming a standard way of doing pub/sub. And what's interesting about Kafka is that it, in contrast to earlier pub/sub and message-oriented middleware systems, it kind of looks like a data system. It was built by, data people. It's modeled after database logs. And then there are all kinds of streaming data sources even within the data center, like, the log of a web server, or a microservice, or even the transaction log of a database. They're all streaming data. How much is your data worth? This is kind of an answer to the question of why should I deal with streaming data? Streaming data is inherently very recent data. That's how data arrives. It arrives kind of coming out of a network adapter. And so some of the most valuable data is streaming data. If you look at the financial world, information about a stock that is 10 milliseconds old might be, a million times more valuable than that same information if it's delayed by a minute. So obviously some data has, some data is never valuable, but some data has a pretty uniform value, but some kinds of data, decrease rapidly in value. So, and the other thing about recent data is it's hot in the sense that it's just arrived. It's probably more likely to be updated if it's just arrived, and it's more likely to be read. So that kind of data is probably, for those reasons, it's probably likely to be in memory. And then as data gets kind of old, it gets colder, it's kind of makes more sense to put it onto disk or cheap storage. The streaming, Kafka and streaming data allows us to think of all of this stuff as data. And you could kind of say data's the new oil. Data powers the enterprise. Some enterprises claim it's the most valuable asset in the enterprise. So if we can have a way of kind of bringing all this data together so that we can combine new data and old data, data in flight and data at rest, then potentially that data is even more valuable than if we look at the two kinds of data separately. So that's an argument for why we should have streams. The kind of flip side of it is why query them? Why treat streams as databases? There's a kind of well-known property observation the duality between streams and databases. A database is simply the sum over time of a stream. It's a cache of the stream. Or the flip side of that is the stream is just the kind of the changes, the change data capture that triggered the deltas to the database. In other words, the information content in the two is the same. It just helps sometimes, for some applications, it helps to think of it as a stream. In some places, it helps to think of it as a database. What we found in databases is a declarative approach is really useful. Using a language such as SQL, a high-level language is a useful approach. So the question at least should be asked, are there benefits of applying a database approach to this data? And then making the difficult case, why SQL? So SQL's got a lot of negatives about it. It looks really old. It's got a char data type. You can define a data type char20, which says this data has to be exactly 20 characters wide. And this is kind of back to the days when data used to arrive on punched cards. It's related to COBOL data types and so forth. So SQL, and people tend to write it in uppercase as if it's kind of shouting at you. So it kind of shows its origins in the world of Fortran and COBOL. You can see that it's 40 years old. And hey, it's just an API to the database, so it's just easy to design a new API. Surely, there should be a better thing. Well, if you kind of look below the surface, there's a lot of things that you get with SQL that you may not even be aware you're getting. So first of all, it's declarative. You ask for what you want, not how to get it. When you join two tables together, you're telling the system, I want you to form the Cartesian product of the employee table and the departments table, and then look for all the rows where the employee department number happens to be the same as the department number. And then throw away the ones where that's not the case. You don't literally want it to form the Cartesian product, but the database system is smart enough to realize that what you're asking for is a join. So, even the most rudimentary SQL database has to have some kind of query planner or optimizer. But once you've got that optimizer, now you've got this. In order to build an optimizer, you have to build a mathematically sound language in order to reason about this. And now you get this system where you're able to change the organization of your data, have the system kind of self-tune, and you can reorganize the data and not tell your application. You can just carry on running the same SQL queries, even though you've moved the data to a different kind of file system, you've re-indexed it, you've perhaps changed the data types of some of your columns. The SQL will carry on working. This is all very useful stuff. This is the kind of stuff that makes software bulletproof. Let's look at the kind of workloads which exist. There's no such thing as a kind of standard SQL workload. There's a variety of workloads. Batch processing, transaction processing, searching for a single record out of a billion based on a text phrase or perhaps some criteria. Interactive, where we're perhaps doing OLAP and we're aggregating data, slicing and dicing. I think potentially streaming data can be added alongside those workloads. Continuous load or continuous ETL is another possible workload. Complex event processing, where we are looking for particular patterns and generating alerts, which then become perhaps messages or, pager messages or emails or something. The SQL already encompasses a wide variety of workloads, and we can happily add streaming to that. We forget that the user or the CIO or somebody is not really thinking about, is this a streaming problem or is this a batch problem? They're just saying, hey, I've got this valuable data, how do I get it? So what I'm trying to do here is building a SQL standard. I'm not going through NC, ISO, well, at least not at this point. I'm trying to build a consensus among the people that are building these interesting data systems, which, as it happens, most of them happen to be open source, and a lot of them are in the Apache Foundation. As part of the Calcite project, we're providing some leadership and some software, but really I'm trying to get a discussion going. Several Apache projects have already signed on and are using Calcite's SDK to build this kind of stuff, but my real goal is to build a consensus about what this language should look like. And if it turns out we're wrong, let's figure it out now. What I don't really want is people creating SQL-like languages, because SQL-like languages are just a curse. They look like SQL, but they don't interoperate very well. The standard tools can't use them. Let's go all the way and make a real extension to SQL. And then we can start building engines which differentiate each other by better quality of service and better performance and so forth. So let's look at some simple queries. The top query is a regular, I don't even know what to call it. Is it a relational query, a traditional query? It's a non-streaming query. Products is a table. We're after all products that have a less than $20 per unit. The bottom one is a streaming query. The only difference is the word stream. So we're reading from the order stream. We're looking for orders that comprise more than 1,000 units. The difference is the top one will run and, for a couple of seconds, give you some data, then stop. The other one will run continuously. You might not get the first record for a couple of seconds, but it will run forever. So you're reading from this infinite pipe, basically. So yeah, the query never terminates. And actually, I lied in the previous slide. Orders is not a stream. It's not a table. It's actually both. So depending on how you use it, you may be interested in the historical orders, all the orders that have ever been received since negative infinity up to the current point. That's called the orders table, right? Assuming the orders table is append only and we never delete orders. Whereas if I'm interested in all orders from now till the end of time, then I use the order stream. And the stream keyword is really the only difference. That is a clue to the system whether I want a continuous query or a historical query. Now, it's possible that one system may not have, it's possible that orders is only a stream and we're not keeping the history of it. That's kind of an implementation detail or a tuning detail. I'm interested in a language that can at least express the idea that that we have both the future and the past of the orders stream. So here's a query where we have both the future and the past of the order stream. And this is actually a very useful pattern of query, because someone once told me that there's no such thing, no useful metrics. All useful metrics are dimensionless, which means they're a ratio. Is it good to know that stock XYZ is trading at $20? Well, it really depends on what its historical average has been. So you need historical context to kind of normalize the data. So this is an example of a query where we're looking at that for orders that are, where the order size is larger than the average size of that order of that particular product over the last year. So we're joining the order stream to the history of the order stream. Now, is that the history of the order stream, is that stored in a table or is it stored in memory? Again, not really my problem. It's an implementation detail, how the system is going to optimize that. Maybe we want to have the system maintain a materialized view of orders over the last year or over the last hour. I don't know. That's an opportunity for whoever's writing the engine to write, a better engine. What I'm concerned with here is the semantics of the language. Is it clear what we want here? And I think it is. So, yeah, just trying to nail down the semantics of streaming queries. I'm not going to get into formal semantics now. There was a lot of work done about 10 years ago. Jennifer Widom and others did some great work on a language called CQL, Continuous Query Language. I'm kind of building on those principles. I'm going to express it in simple terms that what I'm aiming for in streaming SQL, well, first of all, that it's a superset of standard SQL. And in fact, we don't change anything in standard SQL that's already working. If there's a mechanism in SQL, let's not add a new way of doing it. So one of the things that Widom put in her work was a time window attached to the relations in the from clause. I don't think that's necessary, so this isn't in streaming SQL. I might be proved wrong. But the basic idea is that if you capture a stream and you put it all in a table, and then you run the streaming query against that table, you should get the same results doing a regular relational query as you get as if you execute the streaming query. It's a pretty simple idea. Now, of course, the streaming query, you'll have to wait until all the data's arrived. But what that implies is something like, if you're doing a stream-to-stream join, the stream-to-stream join shouldn't give you different results. If one day you run it, this record happens to arrive from the left-hand side before the record arrives from the right-hand side, and the next day the records arrive in different order. So the output of that query should be stable against stuff like arrival times. And by the way, a lot of the stuff I'm saying was said earlier in the Apache Beam talk. Even though they're talking about an API and I'm talking about SQL, I think we're both talking about having a kind of common algebra for streaming. So a lot of the ideas kind of converge. Obviously a streaming system has to, triggering schemes are very important, and some schemes would allow you to emit a record at 11 o'clock with the total between 10 and 11. And then if some data arrives late, then it would perhaps restate the total. So there may be temporarily incorrect results, but the idea is eventually you end up with a correct result. So another principle here is it's kind of useless to have a streaming query where the system can't produce any result until the end of time. So it's kind of a practical consideration that any system should just refuse to accept a query where, well, maybe you want the system to just sit there and the cursor will just blink at you, but probably the system should just reject the query. So in practice, this means that queries have some kind of a time component in them. It's not reasonable to say how many orders are there of product 100, because we've not yet received all the orders of product 100. So usually there'll be something like, how many orders were there for product 100 over the last hour, or the last day, or something like that. There are various ways of kind of getting that assurance that the system's making progress. Monotonic expressions, in other words, increasing expressions, like if we know that one of the columns always increases in value, that's one way, because we can kind of just detect when we've reached 11 o'clock. Punctuations and watermarks are another. There's a variety of ways. I'm not kind of specifying what those ways are. Well, let's just kind of go into a little bit more detail of what those are. And apologies for those of you that sat through the Apache Beam talk. I've reversed the axes. This is not intentional, but they put the event time on this axis, I believe. Anyway, the idea is, so if we're using the monotonic rule, the basic idea is we get a record at, the record arrives at 10:30, or it arrives at 10:30 timestamp 1029. That's record number 3. If a record then arrives that is timestamped earlier, we throw it away because it's out of sequence. So in kind of in the language of Apache Beam and Google Dataflow, the kind of the timestamp of the record is the watermark. And you may be okay with dropping out of order records. You may not be, but it works, and it's simple to implement. The other is this is closer to what my understanding of what would happen in Beam, where you could you're interested in calculating the total between 10 o'clock and 11 o'clock, and at 10:20 you could output a partial total of where we are. So, and of course it would only have records 1 and 2. And then you could emit another total at 11 o'clock and you could restate the total again at 11:15. Record number 6 would never appear in that total because it's timestamped after 11 o'clock. But in this particular scheme, we would allow out of sequence record number 4, and we would also allow record number 7, which arrives well after 11 o'clock, even though it is an event that happened before 11 o'clock. Variety of ways of aggregating, or what people call windowed queries. There's a variety of patterns that it depends on your business case what you want to achieve. there's group by queries where every record contributes to one and only one group. A multiple group by is where a record may contribute to multiple groups. For example, if we're interested in computing, emitting a window of the total, every hour emit the total of the last 3 hours, then any given record will appear in 3 subtotals. And then there are window functions which move over a sliding window. So group by obviously reduces the total number of rows. A multi-group by probably reduces the number of rows, but maybe not. Whereas window functions, which is in standard SQL as the over clause, the same number of rows come out as come in, but there are extra columns. So you could imagine, for example, a stock trade. Every stock trade goes in, and we output, in addition to when the trade happens, how many stocks were bought, what was the price. We can also add on to that what was the moving average of the price of that stock over the hour before that particular order took place. So 1 million records per second in, 1 million records per second out. Kind of very different to, the behavior of group by. So here's group by. I'm going to take you through some of the common patterns in SQL to see how they appear in streaming SQL, and the answer is they generally look very similar. So the stream keyword tells us it's a streaming query, and because we want to make progress, there's going to be a time component in the group by clause, and sure enough there is, floor of row time to hour. So, the 1017, let's see, the 912 record will go in will be rounded down to 9 o'clock, and so it'll appear in the hour, the subtotal for 9 p.m., 9 a.m. till 10 a.m. The 1105 record will go into the 11 till 12 hour, and for this particular, we've not outputted it yet because we're still waiting for the watermark or whatever that tells us that we're ready to output that total. Here's kind of a single slide describing the various window types. Similar to the ones described in the Beam talk, although the concepts are the same, the terminology is a little bit different. So tumbling window is the simplest one. Every hour, output the total for that hour. So every record goes into one and only one hourly total. A hopping window may be, for example, every hour output the total for 2 hours. You see these windows are kind of aligned on an hour boundary. A session window is saying, look for a continuous sequence of records that are separated by the gap between 2 consecutive records is no more than an hour. So that constitutes a session. And what's interesting in that is for tumbling windows and hopping windows and a lot of other kinds of group by, you don't have to see the data to know when the window begins and ends. Whereas the session window is dependent on the data. So it's kind of a strange concept for SQL. You'll see in a minute what that SQL looks like. But if you're interested in a session window for, people browsing from California, then the session window might be, or let's say a session window for people browsing from this IP address, the session might be different. The windows that may actually have different boundaries than someone browsing from another IP address. So the actual boundaries of the windows are defined by the data. And then sliding windows is this idea where every record defines its own window. And it might be something like the hour before and after, or it might be the preceding 10 records or something like that. So here's the SQL for these. The tumbling window, there's 2 ways of expressing a tumbling window. At the top is the syntax I kind of gave in the early group by example. Floor of row time to hour, so we're rounding the row time down to an hourly interval. We provide the tumble function, which allows a kind of a more, an easier syntax and allows you to do something like rounding down to a 17-minute boundary or something like that, which is difficult to achieve with the floor function. Hopping window, we've kind of generalized the tumble function to hop, where you can specify not only what is the emit interval, but also what is the amount of, what's the length of the window. And then the session window, And by the way, so tumble is a mathematical function. You know, given a row time, it gives a value, which is the time at which the window starts. Hop is not really a mathematical function, because for a given record, you know, say this record here at 9:10, it's actually going to produce, hop will basically produce two values, which is it'll produce a value of 9 o'clock and a value of 10 o'clock. Those are the kind of the two windows that that particular record needs to participate in. So group by will see those two values and it'll add that particular row to those two different groups. And then session window is even more complicated than that, because it's a long way away from, it's more like an aggregate function than a mathematical function. Session has to kind of look at the data coming out of orders in order to know what the boundaries of the session. So it's more like a, well, it's not a function, it's more like an operator. But it at least fits in with the group by syntax, and you know, is reasonably straightforward for SQL users to learn. In the interest of time, I'm going to skip over this, but that's an example of sliding windows, very similar to standard SQL. I wanted to focus on this because kind of one of the biggest surprises to people when they hear about streaming SQL is that not all queries produce streams. I call it the pie chart problem. Imagine you're writing a user interface. You want to build a dashboard that's populated, that's doing kind of operational analytics. You're interested in how many orders over the last hour have been made for beer, cheese, and wine. You're a web programmer. You're generating a dashboard, so you need to basically make a round trip, execute a SQL statement, get some data, generate a pie chart, and then serve it back to the user. That's not a streaming query. That's a traditional relational query. It happens to be reading from, you know, an in-memory hash table or something that's being populated by a stream, but it's a regular relational query. So, and if you look at the query we're executing, the stream word isn't there. I believe that a streaming system should support, you know, any kind of streaming system, even if it doesn't call itself a database, should support these kind of queries so that we can very easily, it's kind of a standing relation that's populated by the streaming system, because people are going to want to do these kind of things on any streaming system, especially if we're interested in integration with traditional tools like Tableau. That's the interface that they're expecting to speak. Oh, and by the way, how to implement it, again, that's a decision, that's an opportunity for the author of the streaming system to excel. You know, maybe they materialize it, I don't know. I'm not specifying how they should implement it. Joins, there's various kinds of joins, and streams are slippery things, and joins are just difficult to execute, which means on the flip side is they're providing a lot of value to the application. The simplest kind is joining a stream to a table. So we're looking here as the orders as a stream and products as a table. We're interested in finding the list price of a product. Each time we receive an order, we want to know its list price. So we're kind of doing a lookup. A little bit more complicated, let's suppose the price list is changing as we are receiving orders. So let's suppose we receive an order at 9:45. At 10 o'clock, the price of that item is changed in the price list. And then at 10:05, the system crashes, and we need to recover. We want to replay the stream and get the results. Ideally, we would like to get the same list price as we did at the time the order was placed. This is kind of a temporal database problem. It's not easy to implement. In fact, for some systems, we might just say we don't care. We're going to take the cost of the list price of the item at the time when the query is replayed. So we kind of know that the system could work in various modes, offering it's kind of like transactional isolation. It depends on what kind of quality of replay you want to receive. Then lastly, joining a stream to a stream. Again, because it's streaming, there's a time component in it. So we're interested in orders which ship within an hour of being placed. So we've actually constrained the row time column of the orders and the shipments and said, so the order stream and shipment stream can move independently, but they can't move more than an hour apart. So we are able to make progress. If we said join all shipments to the order stream, that wouldn't happen because shipments is a stream. We'd never be able to make any progress. Since I'm the author of Calcite, just want to explain that this is based on relational algebra. Calcite, is able to plan these queries, and the simple way is we break it down into relational algebra. And what Calcite does, how Calcite optimizes relational queries and streaming queries, is it has query transformation rules. In this isn't a streaming query, this is a regular relational query. But there's a filter on top of a join. And the filter uses columns that come from only the Splunk side of the join. So we can push the filter through the join. That's a query transformation rule. It preserves semantics. It's probably cheaper, but the engine isn't really worrying that much whether it's cheaper. The main question is it semantically valid? Does it preserve the semantics? It does, so we can apply more and more and more other rules. So this is what Calcite does. It has a big library of rules that it's able to apply. This is also how we optimize streaming queries. So Calcite is an Apache project. And by the way, with integration with a lot of other Apache projects and commercial projects. And by the way, I just want to give a shout out to Apache. They do an awful lot for open source. They do a lot for, they provide an environment where communities can thrive and vendor interference is not allowed. Everyone that's a member of Apache is doing it as an individual, not as a member of a particular company. So if you guys are interested in doing open source projects, I thoroughly recommend considering doing it under the Apache framework. I'm going to skip through here. Just a remark about our relational algebra. We were able to achieve this just by adding two additional relational operators, delta and chi, one which converts a relation to a stream, another one which converts the stream to a relation. So kind of minimal, a small change to the relational algebra, which means all of the existing principles of query optimization still apply. I'm going to remark that I want to skip through these and get to questions. So, even operations like sort, union, and DML apply in streaming systems with some minor modifications, but they mainly do what you expect. So in summary, standard SQL, streaming SQL extends standard SQL so it can work over both streams and relations, and it can produce relational answers to streaming queries as well. And it's flexible in terms of how you trigger output, whether it's monotonic columns, punctuation, watermarks, and so forth. And things like views, materialized views, standing queries, all apply within the world of streaming SQL. So with that, I'd like to say thank you and ask if there are any questions. Yeah, so there are definitely some operations that are more, if you're joining two large tables together, doing it in batch mode is more efficient because it can sort the tables and So yeah, when you work on batch, you're working on a table which is like a 10-hour window of the stream. So it's not surprising that it ends up looking similar. The SQL ends up looking similar. From an operational standpoint, if you have a batch ETL process, for example, and you run it at 3 a.m. and it needs to finish by 4 a.m., and one night in 20, it's going to fall over, and you get to work at 9 o'clock in the morning and your ETL hasn't finished. That's more painful than having a continuously executing ETL process that's running 24/7. And if there's a problem, you can fix it and get the ETL system up. So processes that run continuously are kind of easier operationally in some ways than processes that just run periodically. So that's kind of an operational reason to do this. And the other thing is, of course, if it's running continuously, it can use fewer resources. It can perhaps run on one node continuously, as opposed to you trying to run it on 30 nodes to fit within that 1 hour load window. So they're both valid. I'm not trying to get rid of batch SQL, but I kind of want to extend the domain of SQL to deal with continuous streaming problems, as well as batch and interactive and all of the other workloads I mentioned.
I seem to recall a paper about Stream SQL, maybe by Mike Stonebreaker, many years ago, like early 2000s or something like that. I was wondering if this is related to that, or is working on it, or just, well, that wasn't quite right, so I'm doing it right this time, or what?
Yeah. There was a lot of research into streaming query languages back then. There was a paper called Towards a Streaming SQL Standard, which Stonebreaker and Jennifer Whittam is a signatory of it, and some Oracle people were on it. You should read the paper. It's some very nuanced arguments about, if I recall, semantics of timestamps and so forth, which is all fine, but it was still full of kind of academic syntax, brackets, and things that just didn't look like SQL. So I'm kind of out there in industry, and for something to look like SQL, it needs to look like SQL. It needs to just have the look and feel of SQL. And obviously, you need to be able to deal with relational data. You don't want a streaming SQL database and a regular SQL database. You need a database that can handle both of them side by side. So that's what I'm aiming for. Because that effort kind of came to nothing. It was 10 years ago, and it hasn't made it into any commercial product. Whereas I think Kafka has created a new interest in streaming. So let's seize the opportunity the second time around. And I'd love to work with the Oracle folks.
Streambase is just a product, and there are several out of them.
I'm sorry?
Streambase has been a product out of Microsoft, at Mike Stonebreaker's group, and has been incorporated. So that's been well done. Second, you make quite an interesting change in the SQL language by tagging the stream property to the resulting set production area, and not tagging it as an attribute from the tables. And that will cause you quite some problems to have the semantics right. If you're going to mix actually queries over streams and persistent tables. That's what all this research activity is all about. And if you want to really understand the problems of streaming, start studying the SQL standard on the windowing section. That's 300 pages of, well, with all respect, crap. Extreme hard to implement, not to speak how to use it. So I applaud for your actually approach to take an industry side approach to it, but there is quite a lot of potential pitfalls you're running into, and it starts by not putting the attribute stream to the proper language component.
So you would advocate putting the stream against the definition?
The stream, even in a Mike Stonebreaker's environment, is a property of a table. So you have a stream table. And the stream table has actually a limited time window in which it's alive. It doesn't have persistent properties. And it allows, and then the next question is how you're going to deal with windows. That could be another property of the stream table. And that allows you to do a lot of actually optimization as you go. So you have create stream table and create temporary table, and you can create table, and these are the three different areas.
Yeah.
And be very careful in that respect.
I'm very familiar with the SQL standard. I've implemented.
Thank you. You are one of the few in the world I know. Actually, you have read the 4,500 pages.
I've read most of them. I've implemented those window functions and so forth. I think Jennifer Widham's work on SQL and so forth, the idea that you can, translate a stream to a table and back to a stream again, is I think was lost in, for example, Streambase, because it was queries only on streams. Really?
Not true.
So
Not
one
true.
more
Actually,
minute.
Streambase used Berkeley DB actually as the engine to get to the persistent part. It's even that back. And then they noticed actually that the combination, the hybrid between actually a Berkeley DB kind of a library extension and the streaming part are going to bite.
Yeah. Well.
So yes, there is a lot of research out there.
And I've read most of it. To my knowledge, Streambase's integration with stored tables was really clunky.
So I suggest the two of you should take it offline, and we shouldn't be like.
Okay.
All right.
Any more questions?
So yeah, I would propose to just finish because it's past 5, and then people can ask questions offline if they want. So Thank you very much.
Thank you.
And just a reminder for tomorrow, we are starting at 9 as today and yesterday. And after lunch, we are planning kind of a small meeting. Everyone is invited, whoever wants. Kind of a brainstorming about the next XLDB, what sort of topics we want to discuss. Maybe some people want to moderate things. So basically, we will discuss these sort of things with no agenda, nothing structured, just the brainstorming. So again, think about it, plan your time, and maybe you will want to stay for an hour or two longer after lunch and help us with the future meetings. All right, thank you very much, and see you tomorrow.